AC circuit concepts, pure inductive circuits. For Ohm's law, if you can recall, we have V equals IR. Now, if voltage and current are out of phase, contrary to the purely resistive circuit, so we have this expression. Okay, take note, these are complex numbers. So the one we have before is resistance is equal to voltage over current. Now you can see we have here impedance is equal to the polar form of your voltage and then your polar form of your current, where the phase angle of voltage and theta are not the same. So we have this impedance. So this impedance is equal to the real number. That real number is we call resistance, and then the imaginary number we call this one inductive reactance. In this case, because this is inductive circuit, purely inductive circuit. So here it's very important to take note that the angle difference of your voltage is greater than theta. Okay, or the difference between the angle voltage and the angle of current is positive, meaning for pure resistive, if you take note, so our inductive reactance is 0. Okay, because the angle of your voltage and then angle of your current are the same, giving the angle difference equals to 0 degrees. So therefore the impedance is simply equal to resistance. Now for purely inductive circuit, so the phase difference between the two angles, we have 90 degrees, meaning that our resistance is equal to 0. So therefore our inductive reactance is expressed by this value, the angular frequency times the inductance. Okay, so for more information for the inductance, so we can talk about this in the electromagnetic subject. So we have this impedance is equal to the imaginary number XL. Okay, so JXL. So for purely resistive, only a real number, while in a purely inductive, we only have a only imaginary number. So yeah, let's define. So we have here a circuit with an AC voltage source expressed by the instantaneous voltage and then instantaneous current, and an inductor can be expressed with a wire or a coil of wire. So in this case we have a coil of wire. So now the expression of your inductive reactance is JWL, or the angular frequency times the inductance times the imaginary number. So we can express that one in a signal. For example, we have here the amplitude of your voltage signal, then you have your current signal, but this is, if you notice, they are in phase, but for a purely inductive circuit it is out of phase. Okay, so the current is lagging to the voltage, or the voltage is leading current by 90 degrees, or the current is lagging by 90 degrees. Okay, so they are not in the same phase. So we have here the polar forms or polar expression based on the Ohm's law, that the impedance is equal to voltage divided by current. Now if you look at the Phasor diagram, so the voltage M, based on the plot or the graph of the signal, so the voltage M is at 0 degrees, while the IM or the current is at negative 90 degrees. Okay, so this is the Phasor diagram. So this is our basis for our here in the expression, impedance is equal to voltage over current. So we have here Vm angle 0 degrees divided by Im angle negative 90 degrees. So if you perform complex number operation, so we can derive this one. Okay, where Zm or the magnitude of your impedance is equal to the quotient of voltage and current, and then your angle becomes positive 90 degrees. Now if you take the rectangular form of this impedance, we know that Gm cosine 90 is 0, and then sine 19 degrees is 1. So therefore you have XL is equal to JWL, as we have described from the circuit JWL, no, for the reactance, inductive reactance. So therefore we can also express the impedance into a rectangular form, which is 0 plus JWL. So if you notice, our resistance is equal to 0 because this is a purely inductive circuit. Now you might wonder how come the voltage is always at 0 degrees. Okay, most of the time, most of the books, they will treat voltage always at 0 degrees. But if you can find some systems that the voltage is not 0 but completely 90 degrees with the current, okay, and then at the same time leading compared to current by 90 degrees, then that is a purely inductive circuit. Okay, as long as the phase difference between the voltage and current is equal to 90 degrees. Okay, regardless if your voltage is at 0 degrees or any angle. Okay, as long as your phase difference is 90 degrees. So you take note of that, the impedance and the phase difference, as well as the inductive reactance JWL, where W is the angular frequency, L is the inductance. That's it for the purely inductive circuit.